Now, how are we going to integrate? So how are we going to go from a given function to the general antiderivative? Well, the first thing we're going to do is we're going to invert differentiation rules, right? So we have a whole bunch of differentiation rules. We can begin by integrating those. I'm going to show you some examples of how that is done now. I'll show you some more in the video on examples, and then and then you're going to discover some more on your own through class exercises as well as your own work. So for instance, the coefficient rule. We have a coefficient rule for derivatives. It looks like this. If we're taking the derivative of something that looks like a constant or coefficient times a function, well, we don't worry about the coefficient. It stays there. We just differentiate the function and multiply by k. So in other words, when we differentiate, the constant coefficient or a coefficient in front doesn't really play any role. It just stays there. Well, that means, of course, that it will stay there also when we integrate. So that means that if we have a coefficient in the integrand, we can simply take it out of the integral. What about the addition rule? Where the addition rule for derivatives tells us that if I take the derivative of a sum of two functions, that's the same thing as taking the derivative of each of the two functions together and then adding them up. Well, what that means is that the same is going to happen for integrals. So the antiderivative of a sum of two functions is the same as the sum of the antiderivatives of the two functions together. Okay? For the exponential rule, for instance, we know that the derivative of e to the x is e to the x, and therefore the antiderivative of e to the x is also going to be e to the x, of course, plus c. Now notice in the previous two formulae I did not write plus c, and that's because the previous two formulae simply change one integral to a different integral, but they still require an integration to be performed. So the constant, this addition constant c, is still in there, only hidden inside the integral sign. What about trig rules? Well, we've seen one already. Well, let's review it again. So we know that the derivative of sine x is cosine x, and that tells us that the antiderivative of cosine x is sine x plus c, as we saw earlier. Okay. Again, I will invite you to find more of these rules, and we'll do some of them in class, and I do recommend that you do more on your own. In each case, what you want to do is you want to start from a differentiation rule and see what you can come up with by inverting it in terms of integration rule. By the way, because integration is an inverse operation, like all inverse operations, is going to be more complicated than the direct one. So integrating is going to be more complicated than differentiating. Also, we're going to see that while derivatives, well, we can pretty much compute derivatives of anything or any basic enough function. For integrals, is not going to be the same. For some functions, we will not be able to compute the integral. So be prepared for a little bit of extra work as well as some surprises. And here is the one thing that I wanted to mention that you probably have not seen before. There is a little issue, technical issue, that I want to bring to your attention. I want you to know about it. We're not going to be too fussy about it in the actual applications, but I want you to be aware of it and be able to pull it out whenever you need it. And that has to do with discontinuities. So let's say that we have if we want to integrate a function that is not continuous. Just for simplicity, let's say we have a function like that and say it has a vertical asymptote at x equal a. Okay? Now, what I can do is I can still compute the antiderivative of the left-hand side and the right-hand side, okay? But as I do that, those two antiderivatives, the two pieces that correspond to the two pieces of the given function, can be moved by the constant by different amounts. So in other words, I can look at this one as the basic antiderivative or a basic antiderivative, but then what I can do is I can take the left hand side and move it up and take the right hand side and move it down. Now this is again another antiderivative for the given function. The slopes are exactly the same, so the derivative of this new function, this shifted function, will be the same as the original one. Or I can go the other way around. I can move the left hand side down and the right hand side down as well, or wherever I want it, and again I end up with a different antiderivative. So what that means is that when I have a discontinuity, the different pieces need to have different constants attached. So when I'm looking at the antiderivative of f of x, I cannot simply say that it's something, some capital F plus c, but I will have to say that it's going to be some capital F of x plus c1 if x is less than a, and capital F of x plus c2 if x is greater than a. So in other words, I can have two separate pieces be moved by different amounts. As I said, this is not going to be a big issue. In general, I will be happy and will be accepting if you simply write you compute one antiderivative and simply add a c, but there may be some situations where this will come into play, and I will expect you to know that.